Hey everybody, welcome back to Info 3370, studying social inequality with data science. We're continuing our brief introduction to machine learning methods for prediction, and today we'll be talking about random forests as implemented in the GRF package for R. The GRF package is a super powerful package that comes with lots of resources. This is the landing page for their package. Many thanks to the developers who've made this page and the whole package possible. If you get excited about random forests, I'd encourage you to look at some of their tutorials and perhaps read some of their papers under algorithm reference. This is a space of applied statistics that's growing really rapidly, as this package in particular allows you to apply random forests not just for prediction, but also for things like conditional average treatment effect estimation in causal settings. So it's a great resource. Today, we'll start, as we always do, by setting up our environment. So I'm going to copy this code. I've got this over here. You might have to set your working directory to the place where the data are stored. If you're jumping in this video is part of a course, and we've talked in previous classes about how to access the data for a challenge where we predict respondents' annual incomes using data on their parents' and grandparents' incomes, among other variables, using the panel study of income dynamics. So look back at a previous class to see where you can get those data. As always, we'll start by loading the tidyverse and loading here the GRF package that we'll be using for estimation. Then we'll load the learning and the holdout set for our prediction task. Again, see that previous class for more info on those. Okay, why would we want to use a random forest? We began our discussion of prediction by using ordinary least squares, where we predict an outcome as some linear additive function of a set of predictors. That's great, especially when we have a very small sample size, but it can leave us wondering about interactions. Perhaps we think that the response to one variable depends on the values of other variables. It can also leave us wondering about nonlinearities. Perhaps a numeric predictor is not linearly related to the outcome. Maybe the outcome has a sharp jump at some point along that predictor, or a whole series of jumps over the space of that predictor value. Random forests are an excellent tool in settings where we expect lots of nonlinearity and deep interactions involving many variables at once. The base of a random forest is a decision tree. Here I'm showing you one hypothetical decision tree. To think about a tree, you've got to break yourself out of the linear model mindset and think in a whole different way. So let's start with a whole population of units. The algorithm then asks itself, how can I split this population into two subpopulations with very different average values of the outcome? In this case, it might look over all the possible variables on which to split and decide that G2 log income, that's the parent's log income in this data set, is a good one to split into subpopulations. And it might say, well, those who have a parent log income less than or equal to 11.49, they tend to have one value of the outcome, and those for whom that statement is false tend to have a different value of the outcome. And so it makes a split into these two subpopulations. Then the decision tree continues on down the chain. So among the subpopulation whose parents' log income is less than 11.49, it then says, well, there's also a big difference between those whose income is even lower, less than 10.24, versus those whose income is not. So for those whose income is lower, in the learning set there are only 8 such cases, and their average outcome is 10.54. We call this purple node a terminal node. So if a person comes down this tree and they go, yep, my parents' log income is less than that value, yep, it's also less than that value, then the tree would predict for them that their own income as an adult would be on average 10.54. Now, meanwhile, if it was false, then we would go down here. So here we have people whose income is between 10.24 and 11.49. Then it further splits along their parents' income. All of these splits on this side of the tree happen to involve only parents' income. So here it's capturing nonlinear, discrete jumps in the response surface as a function of that continuous predictor, parents' income. Now let's look at the right side of the tree. If your parents' log income is greater than 11.49, then this first statement is false, and you come down here. Again, the algorithm has looked across all the variables to find a way to split this subpopulation into two further subpopulations who have very different mean outcomes. And in this case, it decided to split on education. So for those whose education is equal to high school, they're coded 1 on this variable, and so this statement is false and they drop down here into this terminal node. If the statement is true, they drop down here. And so you see how a person can be dropped down this tree to land at a terminal node of people who look identical to them along all the decisions that led to that terminal node. Decision trees are great because they can capture deep interactions. In this tree, it happens that the only 2 variables chosen are parents' log income and the respondent's education. Actually, that's not true. This is the parents' education here and the respondent's education here. More generally, you can imagine there might be different variables at every step of the way, so that the decision that someone would land at a particular terminal node might be an interactive function of, say, 4 or 5 other variables that lead along the path down to that node. Decision trees are super interpretable, even though they're very different from linear regressions. Because you can look at them and see the interactions, you can imagine taking a new case and dropping it down the tree and knowing exactly why you would make a prediction for that case. You would predict because the leaf that it falls in is the same as the leaf that a bunch of training observations fell in, and you're going to predict for that new case the mean outcome among the training cases. The problem with decision trees is that on their own, a decision tree is a weak learner. It doesn't predict all that well. It's also highly sensitive to the particular sample used for training. So in an important paper, Leo Breiman showed that decision trees could be combined together in an ensemble of trees. In particular, you can grow what's known as a random forest, where the algorithm first takes a random sample of observations. Then it takes a random subset of the variables. And within this new hypothetical data set, it fits a decision tree. Then it sets it aside, draws a new random sample of observations, new subset of the variables, and then it fits a decision tree there. The algorithm does this perhaps thousands of times, producing thousands of decision trees. The prediction that comes out of the forest is then the average of the prediction that you would get by passing a given observation through all of those thousands of trees. Thus, the forest is the average of the trees. It's an ensemble of these many weak learners. As you can imagine, this is quite complicated to actually implement yourself, but thankfully it's not that hard to implement because packages have made it possible. So if we scroll down here to the application, you'll see what you'll need to do to run a call. So in this case, we're going to use the regression forest function in the grf package. So I'm going to go ahead and pull up the documentation for that function. We see here that it's used to predict mu of x, which is the expected value of the outcome y, given that the predictor's x takes some particular value, little x. The arguments, as in some other functions we've looked at, don't take a model formula, but instead they take a matrix of predictors x and a vector of outcomes y. So the first step to use this function is to create that matrix of predictors and to create the vector of outcomes. So popping over to the website, we might create the matrix of predictors by first choosing a model formula. Here we're going to predict the respondent's income as a function of race and sex, education in every generation that we have, and then the log incomes of their grandparents and parents. So let's create that model formula. Then with the model formula, we can now create the matrices of predictors in the learning set and the holdout set by using that model formula with the model matrix function that we've used in previous classes. So you can go ahead and run those lines, and you now have your matrices. We could look at this and see that X learning has 15 columns and 1,365 observations. X holdout also has 15 columns and 1,365 observations. The next step is to create this vector of outcomes. Now recall, we don't have the outcomes in the holdout set. That's what we're trying to predict. We just have the vector of outcomes in the learning set. So here we can define that vector of outcomes, create a new object y learning, which is going to look in the learning data frame and pull out the variable G3 log income. This is the respondent's log annual incomes. So we can look at that, and here we see that y learning is this big vector of numbers, and it has one number for each of the 1,365 cases in the learning set. So now we're getting close. So now we're going to estimate our random forest. So to estimate the random forest, we use the regression forest function, which I have the help file over here. So you're going to call regression forest, tell it your matrix of predictors, your vector of outcomes, and then I would recommend you tell it to tune all of the parameters. There are some hyperparameters in the forest that have to do with, say, how deep the trees are, basically how hard it's going to go after discovering the relationships in the data. And the parameters you pick might have big impacts on how well your model performs. You could possibly, in your application, do something yourself to choose the best parameters, but if you don't have a lot of ideas right now about that, I think a good default is just to let the package choose the parameters itself. They've put a lot of thought into how to search over the parameter space and quickly and efficiently find some good hyperparameters for you. And you'll see how quick this goes. I'm going to run this fit right now with our 1,365 cases, and it's already done, estimated that random forest. Unlike other models, it's a little hard to look at a random forest. It's kind of a black box at this point, but to predict from the random forest is not that hard. So let's predict in the holdout set. For this, I'm going to come back over here to the web page and pull this code for making the predictions in the holdout set. So we're creating here a fitted.grf object. This is an object that stores predictions from our fitted model fit using the new data X holdout, which is that matrix of predictors for every observation in the holdout set. So we've got our fitted grf object, and then we can now take this, and if you look at this, it is actually a list where the first element is predictions, and if we call fitted grf $predictions, that's going to give us a vector of predicted values. So we can take the holdout set, create our new variable g3 log income, where we're going to stick in that vector of fitted values. And that's about it. You could now select, if you wanted, to the identifier and the predicted values. And this data set would be ready to go to save in a CSV file and upload as part of our income prediction challenge. So I hope you've learned a little bit about how to use regression forests. These are super powerful tools, and also they're a great onboarding step toward more complicated generalized random forests you might fit to learn about conditional average treatment effect estimation. But in the meantime, they're a super useful prediction tool, and I hope you'll consider them alongside the other tools we've considered, which were ordinary least squares, regularized regression, and generalized additive models. That's it for today.